Hello, Math 1224. This is Dr. P with Lesson Launch 19.1, Comedy of Errors. So I've put a problem here. Estimate the value of e squared. And that's exactly what I'm going to do. The goal of this video is going to be to talk about how we use Taylor series to do this problem, that is, get a decent estimate for e squared. But then, once we have done that, how do we figure out how far off that estimate could be? Because that's the thing with estimation is when you estimate something, you kind of want to know how far off you're likely to be. I mean, if you asked me to estimate the value of e squared and I said, oh, I'll bet that's about 50, then, well, I've done exactly what you said. I've given you an estimate for e squared. Problem is it's kind of a lousy estimate. In fact, it's a really lousy estimate. It's not even close. So the thing with estimates is, in order for an estimate to be useful, you have to have some idea of how close it is likely to be to the actual answer to the question that you're interested in. So that's what this video is about. All right, so first of all, I want to just do a little bit of review of how we can use the Taylor series to calculate something like e squared. So this is something that we're going to recall for now. By the way, I got a lot of questions about this in the last lesson launch, which I was thrilled to see so many people asking this question. So I claim that e to the x, that is equal to the sum from k equals 0 to infinity of x to the k over k factorial. And a lot of you basically asked, now in the last set of videos we were sort of going in this direction, that is, I was looking at this and inferring that that was e to the x. But some of you were asking, well, how do you know that? And then some people were asking, yeah, we've heard that before, but why is that true? And that's a good question to ask. I'm going to give a very short answer to it here and then try to address this in more detail in class. So here's why this is the case. I'm just going to say this out loud without trying to write all of this down. Okay, so why should we believe this? All right, so the way that we got here is we started by approximating e to the x with polynomials. And when we did that, actually, let me write some of this down. So this is just review. And we were doing polynomial approximations for e to the x. And the idea was we tried to build polynomials that have the same behavior as e to the x at x equals 0. So these are approximations near x equals 0. So the way that we did that was we first said, well, what constant polynomial would have the same value as e to the x at 0? So that estimate was 1. And we said, what polynomial would have not only the same value, but the same first derivative? And that was 1 plus x, because we need a value of 1 and also a first derivative of 1. And then for a second degree polynomial, we said, well, let's try and match the 0th, first, and second derivatives, and we got 1 plus x squared over 2. And the pattern that we discovered in general, let me actually call that not pk of x, but pn of x. Back. Erasing on this thing is super awkward. So the nth polynomial estimate that we got was basically this. I mean, we went back and sort of retroactively identified that there were really factorials lurking in these denominators here. We went all the way up to x to the n over n factorial. And we said, that's a polynomial that has the same 0th through nth derivatives as this function at x equals 0. Now, the thing that I wasn't super explicit about was that from there, we do a limiting process. So we say, okay, what's the limit as n goes to infinity of Pn of x? Well, all of these polynomials here, they're just partial sums of an infinite series. That infinite series is 1 over 0 factorial plus x over 1 factorial plus x squared over 2 factorial plus x to the third over 3 factorial, and so on. It's an infinite series. And these p sub n's are partial sums of that. So we said, well, these approximations ought to be getting closer and closer to e to the x. And so for that reason, we say that this sum here, the limit of this sum, is e to the x. But I will fully and freely admit that I didn't prove that. I didn't give an absolute proof of it. The best I did was to give you a Desmos demo that showed that lovely golden retriever tail on the left sort of flipping and flopping, but near 0, these sums were getting closer and closer to e to the x. And that's the only basis on which I'm asking you to believe that right now. That's we could actually do the exercise of computing the sum of the series for some value of x, or rather computing estimates, because we can't compute the sum of an infinite series directly. But we could compute estimates for this value, pick some value of x, compute out the first 10 or so terms of that series, And we would see that we get something very close to e to the x for that value of x. And that's the basis on which I'm asking you to believe this. To learn this with any more certainty with that, you would need to take a course in real analysis, which is where we prove a lot of the things that we're using in calculus. Okay, so now I'm 5 minutes in, but I figured that was something that we probably should talk about, given that there were quite a few questions about that in the last set of videos. Okay, so anyway, how do we apply all of this to get an estimate for e squared? See, I think I can actually spin this into something useful for what we're doing now. All right, so suppose I want to calculate e squared. Well, that means that e squared is the sum of this infinite series here. 1 over 0 factorial plus, now here we're saying x is equal to 2. That means we're going to substitute the value x equals 2 into this series here in order to get the value of e squared. So that means e squared is the sum of this series. So what I'm going to do is I'm just going to calculate out a few terms of this series here. I think what I'll do, just so that we have something to work with here, I'm going to compute out the sum of all of these terms here and try and get an estimate. All right. I do have my calculator nearby in case I need it, which for this I might. I think I've given myself quite a task here, actually. Anyway, so it looks like what I'm going to get is 1 plus 2, and then 2 squared over 2, that's another 2. And then 2 cubed over 3 factorial, that's 8/6. So that's going to be, what is that? I think that's 4/3, so that's 1.33. And then 2 to the 4th over 4 factorial, that's 16 over 24. So that's actually kind of convenient because that's 2/3. That's going to join up with that previous term to give me another 2. And then 2 to the 5th over 5 factorial, that's 32 over 120. I'm doing the math in my head here, but I think it comes out to 4/15. And, good gracious, what's 4/15? Well, I know 3/15 is, yeah, you know what, I'm just going to write down. I think this is 0.27. You can check my math on that using a calculator if you want. So I think this is going to come out to, oh, by the way, I shouldn't say this is equal. I should say this is squiggly equal, because this is not the entire sum. If I had the entire sum, that'd be equal, but I'm just approximating here. So I think I've got, let's see, 1 plus 2, 2, and another 2, and then 0.27. So I think that's going to give me 7.27. So now what I'm going to do is I'm going to figure out how far off I am in the cheapest way possible. The cheapest way is to actually use a calculator. So you can't see me doing this, and I've discovered that when I pull up apps on this during the videos, it doesn't always show what I'm doing. So instead, I'm just going to talk to you while going over to my laptop here, pulling up Wolfram Alpha, and asking it, what is e squared? And actually, that's I got a pretty nice result here. So according to Wolfram Alpha says that e squared is 7.389, almost exactly. There's a little bit of change there, but 7.389 is the actual value. So you got to admit, pretty impressive that just by doing rational number arithmetic, we were able to get such a good estimate for e squared here. So this is our estimate, and this was the actual value. So now here's a definition, and then we're going to talk about the issue of how we figure out how far off we are in the next video, because I'm already getting a little long-winded here. Need to get a drink of water, or maybe a soda or a beer or something. Anyway, I want to talk about what we call error, because it might be different from the way you've referred to error in other courses, especially science courses. So in this course, when I ask for the error of an approximation, what I'm asking for is this: the actual value of f at whatever point we're trying to evaluate it at, minus whatever Taylor approximation you're using evaluated at that same value. That's the error, okay? That's the error of this estimation. So in this case, my f of x was e to the x, and then my p sub n was, I believe, the fifth degree Taylor polynomial. So that was that thing above. And then my a was equal to 2, because that's the place where I'm trying to evaluate all of this stuff. Okay, so in this case, my error would be actual e squared minus the fifth degree Taylor polynomial at 2. All right, this is turning into a real cookie chill out here. So that error is going to be about, based on Wolfram Alpha, it's going to be about 0.12. That's my error for this estimation. Okay, now the reason I said this is different from what you may have encountered in your science courses is, at least, I don't know where you grew up, but where I grew up in Weatherford, Texas, we took science courses like physics AP course, chemistry AP course, and we always said that the error, so I'm going to put in other courses and then also a question mark, because maybe y'all did it correctly in other courses. I don't know. But when we talked about error in other courses, we said that the error, that is your actual error, not your relative error, like absolute versus relative. The error was your estimate minus the actual value. And the reason for this was if your estimate was an overestimate, then you had a positive error, like you were, this amount over. And if your estimate was too low, then the error is negative, which tells you that you were a little bit under. Now, when I say that my error is 0.12, I'm saying that the actual value is higher than the estimate I came up with. And the reason for doing that is that I want to be able to do the following thing. I want to be able to say that the actual value of the function at A is equal to the nth Taylor polynomial at A plus this error term. So in this case, I had e squared, the actual value of e squared is equal to my estimate, which was 7.27, plus this error, which in this case was about 0.12. Okay, so the reason we define error that way instead of the other way around is so that we can talk about this error term here. And that error term will be positive if the actual value is higher than you estimated, and it'll be negative if the actual value is lower than you estimated. Okay, so that's the definition of error. That was quite the comedy of errors there. I think I've delivered on my promise. In the next video, I will talk about how we actually determine the maximum possible error. Very exciting stuff. Stay tuned.